right now, floating in the freezing pitch black void just past the orbit of Neptune, there might be a massive invisible rocky planet.
Yep, roughly 5 times the size of Earth.
Exactly, and it's just silently herding a flock of icy comets out there. Or, maybe there's no planet at all. Maybe instead there is a primordial black hole, the exact size of a grapefruit, just left over from the very first fraction of a second of the Big Bang, just sitting in our astronomical backyard.
I mean, it really sounds like pure science fiction,
Yeah.
right? But the mathematical reality is that something is out there. It's pulling on the outer edges of our solar system. The gravitational math is basically screaming that a massive object exists. But, well, every time we point our most powerful telescopes into the dark, we find absolutely nothing.
Yeah, we are basically looking at a cosmic ghost, and today we are taking you on a definitive detective story to hunt it down. We're doing a deep dive into this huge stack of comprehensive astronomical research, some historical archives, and the most fiercely debated Wikipedia articles on celestial mechanics we could find. It's a lot of material to unpack.
It is, yeah. But we're going to unpack the search for Planet 9. We're going to look at the undeniable gravitational footprints left at the scene. We'll build a physical profile of what this hidden world might actually look like. And, we'll get into the brutal supercomputer-driven warfare happening right now between the astronomers who swear it's there and the skeptics who think it's all just a massive optical illusion.
And, if the skeptics are wrong and the planet hunters are wrong, we're going to explore the alternatives that require us to literally tear down the fundamental laws of physics to explain what we are seeing.
Right. It is the ultimate scientific cold case. And to understand why astronomers are willing to bet their whole careers on an invisible ghost, we have to realize that finding hidden planets by tracking gravitational wobbles, that isn't a new parlor trick. This is exactly how we mapped the solar system in the first place.
It is.
Yeah.
The strategy of using gravity as a bloodhound has an incredible pedigree. If we rewind to the early 19th century, astronomers had a major problem with Uranus.
So William Herschel had discovered Uranus in 1781, and for decades, observatories tracked its orbit. But it wasn't behaving. According to Isaac Newton's laws of universal gravitation, which were basically sacred text at that point, Uranus should have moved along a very specific elliptical path.
But it was drifting, right? Like it would speed up slightly in certain parts of its orbit and then lag behind where the Newtonian math predicted it should be.
Exactly. The discrepancies were tiny, just arcseconds of a degree. But in celestial mechanics, precision is everything. You can't just brush off a wobble. So the scientific community faced a crisis. Either Newton's laws of gravity were fundamentally wrong at extreme distances, or something massive and invisible was out there in the dark, tugging on Uranus.
Which is, it's like watching a dancer on a dark stage. You can't see their partner, but you can see the visible dancer being pulled, stumbling, being spun around.
Oh, that's a great way to put it.
Yeah, and if you measure how the visible dancer deviates from their solo routine, you can calculate the exact weight and leverage of the unseen partner in the shadows.
That is the perfect way to visualize perturbation theory. And in 1846, a French mathematician named Urbain Le Verrier decided to do the math. He didn't use a telescope. He used a stack of paper and agonizingly complex calculus.
Wow.
Yeah, he worked backward from the wobbles of Uranus to calculate the mass, the distance, and the exact trajectory of whatever was pulling on it. And then he mailed his calculations to the Berlin Observatory, telling them exactly what coordinates to look at.
And within an hour of opening the letter and pointing their telescope, they found Neptune, exactly where the math said it would be.
It was arguably the greatest triumph of mathematical physics in history. It proved that gravity could be used to see the invisible, and because it worked so flawlessly for Neptune, it baked an assumption into the minds of astronomers for the next century. Like if you see a wobble, there is a planet waiting to be found.
Right, which leads us directly into the Great Wild Goose Chase. Because finding Neptune didn't entirely fix the math, did it?
No, it really didn't. Even after factoring in Neptune's massive gravitational pull, Uranus still seemed to have microscopic irregularities in its orbit. And eventually, astronomers started noticing that Neptune itself seemed to be deviating slightly from its predicted path.
Okay, enter Percival Lowell. So in 1906, Lowell, who was a very wealthy, very obsessive astronomer, launched a massive, well-funded campaign at his observatory in Arizona to find what he dubbed Planet X.
Right.
He was convinced he could pull a Leverrier and find a ninth planet just by tracking these residual wobbles in Uranus and Neptune.
And Lowell actually spent the rest of his life looking for it and died without finding anything. But his observatory kept up the hunt. They used a device called a blink comparator, which it rapidly switched between two photographs of the same patch of night sky taken weeks apart.
So if a dot moved between the two photos, it wasn't a star, it was a planet.
Exactly. And in 1930, a 23-year-old farm boy turned astronomer named Clyde Tombaugh finally spotted a moving dot. He found Pluto.
And the world went wild, right? They found Planet X, the math worked again, except it was a total fluke.
A complete staggering coincidence. It took decades to figure out, mostly because Pluto is incredibly difficult to measure. But once astronomers finally determined Pluto's true mass, the bottom basically fell out of the discovery.
Yeah.
Pluto is essentially a speck of ice. It is roughly 0.2% of Earth's mass.
Which means it has absolutely zero capacity to drag gas giants like Uranus or Neptune around. It's like, I don't know, a fly trying to alter the trajectory of a freight train?
Precisely. Pluto was in the right place at the right time to be found, but it was an imposter. It wasn't Lowell's Planet X.
But wait, if Pluto wasn't pulling on Neptune, what was causing the wobbles that Lowell's was tracking in the first place?
Bad data. It turns out 19th century astronomers had slightly miscalculated the mass of Neptune itself. In 1989, when the Voyager 2 space probe actually flew past Neptune, it gathered precise telemetry that allowed scientists to correct Neptune's mass. It was about 0.5% less massive than previously thought. Yeah, so when they plugged that corrected, slightly lighter mass back into the orbital equations, all the wobbles vanished. Uranus's orbit made perfect sense. Neptune's orbit made perfect sense. There were no missing pieces. The ghost was exorcised.
So we have this incredible history. We have the triumph of Neptune, which proves the concept works. Then we have the false positive of Pluto, which serves as this massive cautionary tale about overinterpreting data.
Right.
Fast forward to the early 2000s, and the solar system is neat, tidy, and fully explained. But then the boosts come back. Only this time, it's not the giant planets acting strangely. It's the tiny icy debris out on the very fringes.
Exactly. The focus shifts entirely away from the giant planets and moves into the Kuiper Belt and beyond. In 2003, a team led by Caltech astronomer Mike Brown discovered an object they named Sedna. Sedna is a dwarf planet, slightly smaller than Pluto, but its orbit completely broke our understanding of the solar system.
Okay, to understand why Sedna broke the models, we have to talk about what a detached orbit is. Because most things in the outer solar system, comets, chunks of ice, regular Kuiper Belt objects, they all live in a gravitational hierarchy ruled by Neptune.
Right, Neptune is the undisputed gravitational bully of the outer solar system. It sits roughly 30 astronomical units from the Sun. Just to give a sense of scale, 1 AU is the distance from the Earth to the Sun, so about 93 million miles. So Neptune is 30 times further from the Sun than we are.
Okay, yeah.
Now, most icy bodies might have highly elliptical orbits, meaning they swing way, way out into deep space like a stretched-over band, but when they snap back toward the Sun at their closest approach, a point called their perihelion, they almost always come back to around 30 to 40 AU. They come back to Neptune's neighborhood.
Because Neptune's gravity is what threw them out there in the first place or captured them. It essentially holds the leash.
Right? But Sedna doesn't do that. Sedna's orbit is unimaginably huge. It takes 11,400 years to go around the Sun once. It swings out to about 937 AU. But the shocking part is its closest approach. Sedna's perihelion is 76 AU.
Wait, so it never comes anywhere close to Neptune?
Never. It is entirely detached from the gravitational influence of the known giant planets. Neptune literally cannot reach it.
Which raises an immediate, glaring mechanical question, right? How did it get there? Objects in space don't just magically levitate outward.
They absolutely do not. Orbital mechanics is ruled by the conservation of angular momentum. A planetary body doesn't just spontaneously shift its closest approach 40 astronomical units further out into the void. It requires a massive exchange of energy. It requires a gravitational interaction to physically pull it away from Neptune's influence and strand it out there.
Okay, so let's go back to our pond analogy. Finding Sedna's detached orbit is like finding massive, violent ripples in the dead center of a perfectly calm lake, but there are no boats around and you didn't hear a splash. Something massive had to have moved under the surface to displace that much water. But initially, astronomers didn't assume a hidden planet, did they?
No. Planetary science is conservative by nature. When Sedna was found, the immediate assumption was that its orbit was a relic of the solar system's birth. The prevailing theory was that billions of years ago, when our sun was still part of a dense stellar nursery, a rogue star passed incredibly close to our solar system, and its gravity basically dragged Sedna outward, permanently detaching its orbit.
A hit and run by a passing star. I mean, it makes sense. It's a one-off event, and you don't need to invent a whole new planet. But then Sedna got a friend, and the passing star theory started to fall apart.
Yeah, in 2014, two astronomers, Chad Trujillo and Scott Shepard, announced the discovery of another extreme object named 2012 VP-113. Just like Sedna, it was detached. Its closest approach to the Sun was 80 AU.
So now you have two bodies stranded in the no man's land outside Neptune's reach.
But Trujillo and Shepard noticed something much more profound than just their distance. When they looked at the orbital mechanics of Sedna, VP-113, and a handful of other extreme trans-Neptunian objects, or ETNOs, they realized these orbits weren't just randomly scattered. They were exhibiting a peculiar phenomenon called orbital clustering.
Can you explain clustering for us? Because space is three-dimensional, so an orbit isn't just a flat circle drawn on a piece of paper. It has angles, tilts, and orientations.
Exactly. So picture an elliptical orbit as a hula hoop. You can tilt the hula hoop up or down, and you can spin it so the long end points in different directions. Trujillo and Shepard noticed that a specific orbital parameter called the argument of perihelion was clustering near 0 degrees for these objects.
Meaning they were all crossing the plane of the solar system at almost the exact moment they made their closest approach to the sun. They were synchronized.
Yes. And in a chaotic system 4.5 billion years old, things don't stay synchronized unless something is actively keeping them that way. Trujillo and Shepard were the first in the modern era to formally publish a paper proposing that a massive unknown planet in the 200 to 300 AU range was gravitationally hurting these objects.
Okay, I have to stop here and push back on the core premise. The volume of space we are talking about is mind-bogglingly vast. We are looking at a handful of icy rocks floating billions of miles away from Earth. If you have a massive yard and you find two leaves pointing the same way, you don't assume a landscaper arranged them, you assume the wind blew, right?
Right.
Couldn't these two weird orbits, or even a dozen of them, just be a total statistical coincidence? Why leap immediately to there's a giant hidden planet?
It is the absolute right instinct to be skeptical. The burden of proof for a new planet is incredibly high. And frankly, the idea of a giant hidden planet sounded vaguely absurd to a lot of prominent astronomers, including Konstantin Batty and Mike Brown at Caltech. And keep in mind, this is the same Mike Brown who actually discovered Sedna in the first place.
Oh, wow.
Yeah, when Trujillo and Shepard published their hidden planet theory in 2014, Batty and Brown did not agree with it.
They thought it was a statistical illusion.
They did. Batty is a theoretical astrophysicist, a master of orbital dynamics. Brown is the observational powerhouse. They teamed up specifically to mathematically prove Trujillo and Shepard wrong. Their goal was to run the simulations and show that this clustering was just a fluke, a temporary alignment, or a misinterpretation of the data that would wash away under rigorous scrutiny.
But in attempting to bury the theory, they accidentally became its biggest champions.
They absolutely did. This brings us to 2016, which is the watershed moment for the Planet 9 hypothesis. Batty and Brown decided to clean up the data set. They removed any objects that had even remote chance of being influenced by Neptune, leaving them with only the most extreme, pristine, and mathematically stable trans-Neptunian objects. They isolated 6 specific ETNOs, including Sedna and VP-113.
And when they looked at those 6, the coincidence alignment completely evaporated, didn't it? Because it wasn't just that they were crossing the plane at the same time. It was a multi-dimensional alignment that shouldn't be possible.
Right. They found that the longitudes of perihelion for all 6 objects were bunched together. This means that if you trace the long, stretched-out part of their orbits, they were all pointing in the exact same physical direction in deep space.
Imagine a school of small fish in the ocean. If you see one fish darting to the left, it's just a fish. If you see 6 fish separated by vast distances, all suddenly pivot and swim in the exact same synchronized formation, pointing in the identical direction, your brain immediately knows they're reacting to a predator.
Yeah.
You don't actually need to see the shark in the murky water to know a shark is there. The synchronization of the fish, tells you the exact location and size of the shark.
That is a phenomenal mechanical analogy because it highlights that this isn't passive drifting. It is active herding. But the alignment went even further. Batty and Brown realized that not only were the orbits pointing in the same direction, but they were also all tilted in the exact same direction relative to the ecliptic, the flat plane of the solar system.
So they calculated the odds of this happening purely by random chance, like just a cosmic fluke of the initial solar system formation. The math came back at 0.007%.
7 thousandths of 1%. At that point, statistical coincidence is virtually impossible. The physics demands an explanation, And this is where the genius of Babbage and Brown's 2016 paper comes in. In science, a good theory explains the single anomaly you were looking at. But a truly revolutionary theory unexpectedly solves mysteries you weren't even trying to solve.
It's like finding a key on the street, trying it on a random door, and it doesn't just open the front door, it unlocks a safe you've been trying to crack for 10 years.
Exactly. When Babbage and Brown modeled this hypothetical massive planet to see if it could cause the clustering of those 6 ETNOs, the computer simulations spat out secondary effects. The model showed that Planet Nine's gravity elegantly explained 4 distinct, seemingly unrelated anomalies in the outer solar system.
Okay, let's unpack the mechanics of those 4 fingerprints, because this is the bedrock of the physical evidence. Number 1 is the clustering of the extreme orbits pointing in the same direction, which we just covered. Number 2 is the sheer existence of detached objects like Sedna.
Right. The simulation showed that Planet Nine's gravity acts like a tow truck. Over millions of years, its gravitational resonance slowly lifts the perihelia of these icy rocks, physically pulling them up and away from Neptune's reach, creating that detached population we see with Sedna.
Okay, number 3 is where my brain starts to struggle. The model predicted the generation of high-inclination ETNOs with orbits almost perfectly perpendicular to the plane of the solar system. And number 4 is high-inclination objects with small, tighter orbits. Wait, hold on. Let's break down number 3. How does a single planet on a relatively flat plane cause smaller objects to suddenly tilt 90 degrees and orbit totally perpendicularly? If I have a massive planet violently tilting orbits perpendicular to the sun, isn't that a chaotic system? Wouldn't a gravitational bully just scatter everything into deep space or crash them into the sun? How does a perpendicular orbit survive?
I mean, it seems incredibly counterintuitive, and it was a massive surprise in the simulations. But it comes down to a very delicate, beautiful gravitational dance involving orbital resonances. There is a phenomenon in celestial mechanics known as the Kozai mechanism, or Lidov-Kozai effect.
Explain the mechanism. What is actually happening to the physical momentum of these rocks?
Think of it as a strict mathematical trade-off dictated by the conservation of angular momentum. When a smaller icy body is subjected to the continuous gravitational perturbation of a massive distant planet, it cannot just fly around randomly. If it does, its orbit will eventually cross the path of the giant planet, and it will be either ejected from the solar system or destroyed in a collision.
It has to find a safe rhythm, like 2 kids swinging a cosmic jump rope. The smaller objects have to jump at the exact right time, or they get tangled and destroyed.
Yes, it's a form of phase protection. The secular resonance with Planet Nine forces the smaller objects to make a trade. They trade eccentricity for inclination.
Meaning they trade how stretched out their orbit is for how steeply tilted it is.
Exactly. As Planet Nine pushes on them, their orbits become less flat and stretched and more round and steeply tilted. The math shows that this gravitational shepherding naturally produces a subset of objects that get pushed so far, they flip entirely perpendicular to the solar system.
Wow.
And they cross the plane of Planet Nine's orbit only when they are at their absolute furthest distance from the planet, ensuring they never collide.
And here is the absolute kicker. When the supercomputer spit out this prediction in 2016 that highly perpendicular objects should exist, astronomers had already found them. A few years prior, surveys had discovered bizarre objects orbiting almost vertically, like one nicknamed Drac, standing for Dracula because it was so weird. The observers had absolutely no idea why these objects were orbiting vertically.
It was an unsolved mystery just sitting in the data.
Yeah.
And Babbage and Brown's Planet Nine model naturally produced them without being asked to.
It's like finding a suspect's shoe at a crime scene and realizing the tread perfectly matches a bizarre, unexplained footprint found 3 towns over a decade ago. It ties the whole room together.
And the predictive power of this gravitational model continues to hold up in real time. Fast forward to 2024, Brown and Badgen ran even more rigorous simulations. They mapped how Planet Nine would interact with the background radiation of the galactic tide over billions of years. They found that Planet Nine wouldn't just keep objects detached, it would slowly push a very specific small subset of them back inward, creating objects that cross Neptune's orbit again.
They calculated the exact ratio, right?
Yes. They predicted that if Planet Nine exists, about 3% of these extreme objects should be on Neptune crossing trajectories. If Planet Nine does not exist, that number should only be 0.5%. When they looked at the actual observational data from sky surveys, the ratio was exactly aligned with the 3% prediction.
Plus, just to bring this right to the absolute bleeding edge of discovery, in early 2025, astronomers found a brand new extreme object designated 2023 KQ-14, nicknamed Ammonite. And where was it? It was sitting exactly opposite the main cluster of the other sednoids.
Which is brilliant because an uneducated glance might say, aha, it's on the opposite side. That breaks the clustering theory.
Right. If the fish are all swimming left and one fish is swimming right, doesn't that disprove the shark?
Not in orbital mechanics. The Planet 9 simulations explicitly predicted that a small subset of objects would be trapped in a different gravitational resonance that holds them in a stable orbit exactly 180 degrees opposite the main cluster.
That's crazy.
Yeah, Ammonite perfectly filled a mathematical gap that the model demanded must exist. In the supercomputer, Ammonite's orbit is stable for 4.5 billion years. But only if Planet 9 is out there holding the cosmic jump rope. If you remove Planet 9 from the code, Ammonite's orbit becomes chaotic and destabilizes.
So if we look at this objectively, the gravitational signature is profound. The math undeniably works. But it only works if the shark swimming in the outer solar system has a very specific size, mass, and swimming pattern. Which brings us to the next massive question. What exactly is this ghost world?
Right.
If the math is telling us a shark is out there, what does the shark actually look like? Let's build a physical profile of our suspect.
Well, when Badigian and Brown first published in 2016, they estimated this thing was a true behemoth. Based on the limited ETNO data they had at the time, they modeled a planet somewhere between 5 and 10 times the mass of the Earth, orbiting in a massive ellipse between 400 and 800 AU away.
Okay.
They predicted it took anywhere from 10,000 to 20,000 years just to complete one single orbit around the sun.
At 10 Earth masses, we were talking about an ice giant, right? Like a mini Neptune.
Almost certainly. A 10 Earth mass planet would have a solid core of iron and rock, surrounded by a thick, crushing mantle of water ice, ammonia, and methane, and completely wrapped in a dense, gaseous atmosphere of hydrogen and helium. It would be a dark, freezing, violent world. Surface temperatures would hover around 47 Kelvin.
That's roughly minus 375 degrees Fahrenheit, a place where nitrogen freezes solid.
But science is a continuous process of refinement. The 2016 profile was a first draft. As we discover more of these tiny icy bodies in the extreme outer solar system, each new object acts like a new data point, allowing theorists to tighten the parameters of the model.
It's like triangulating a cell phone signal. 2 towers give you a massive search area, but once you have 6 or 10 or 50 towers, you can pinpoint the phone to a single room.
Exactly. In 2021, Badigian and Brown updated their models based on a larger data set. They shrank the orbit significantly, pulling it down to an average distance of about 380 AU, and refined the mass to roughly 6.2 Earth masses.
But hold on to your hats, because just recently, a 2025 study threw a massive curveball into this profiling effort. Amir Siraj, Christopher Chiba, and Scott Tremaine ran 300 highly advanced N-body simulations using a newly expanded sample of 51 extreme trans-Neptunian objects.
Yeah.
And the suspect they generated looks very, very different from the mini-Neptune of 2016.
The 2025 update brings the mass down to 4.4 Earth masses, with a tiny margin of error. It pulls the orbit much, much closer to us, predicting a semi-major axis of just 290 AU. And crucially, it drops the eccentricity of the orbit down to 0.29.
Okay, let's unpack those numbers because they fundamentally change what we were looking for. First, to put that 0.29 eccentricity in perspective, a perfect circle has an eccentricity of exactly 0. Earth's orbit is nearly 0. A highly stretched out comet might have an eccentricity of 0.9, looking like a squashed cigar.
Right.
So at 0.29, Planet 9 isn't on some wildly unstable, plunging trajectory. It's an ellipse, sure, but a relatively stable, localized one. It stays relatively close to that 290 AU mark.
The study also predicts a very flat inclination, meaning it orbits only about 7 degrees off the main plane of the solar system. But the most shocking implication of the Siraj study is the mass. At 4.4 Earth masses, the physical nature of the planet shifts.
Right, because at 10 Earth masses, you have enough gravity to hold on to massive amounts of primordial hydrogen and helium gas. You become an ice giant. But at 4.4 Earth masses...
At 4.4 Earth masses, you might not have enough gravity to hold on to that thick gaseous envelope during the violent early days of the solar system. We might not be looking at a mini Neptune at all. We might be looking at a massive, solid, rocky world. A super Earth.
A giant rock in the dark. Which is incredibly tantalizing from a planetary science perspective. Because when we point our telescopes at other stars in the Milky Way, we find that super-Earths are the most common type of planet in the galaxy. They're everywhere.
Yep.
Yet strangely, mysteriously, we don't seem to have one in our own solar system. We have small rocky planets and we have giant gas planets. Nothing in between.
It has always been a glaring statistical anomaly in our solar system's architecture. The confirmation of a rocky planet 9 would elegantly resolve that.
But wait, how does a giant rocky planet form or end up 290 astronomical units away from the sun, where
Yeah.
there was barely any raw material to build it?
It didn't form out there, it formed much closer to home. The leading origin story relies on something called the Nice model, named after the city in France where it was developed.
Okay.
The Nice model dictates that our early solar system was a chaotic, violently shifting environment. It suggests the solar system originally formed with 5 giant planets packed closely together: Jupiter, Saturn, Uranus, Neptune, and our mystery 5th giant.
But it was too crowded.
Way too crowded. As the giant planets interacted with the primordial disk of gas and dust, their orbits began to migrate. Jupiter moved slightly inward, while Saturn moved outward. Eventually, they hit a gravitational resonance, specifically a 2.1 resonance, where Jupiter completed exactly 2 orbits for every 1 orbit of Saturn.
And when two massive gravitational forces synchronize like that, the combined pulling acts like a wrecking ball on everything else around them.
It triggered a massive system-wide instability. Uranus and Neptune were shoved outward, scattering millions of icy bodies into the Kuiper Belt and the Oort cloud. And according to the computer models, in this chaotic game of cosmic billiards, the mystery 5th giant planet got too close to Jupiter or Saturn. The gravitational kick it received was catastrophic. It was violently ejected outward.
So Jupiter essentially sank a solid ball, but instead of flying entirely off the billiard table into interstellar space to become a rogue planet, the ball got stuck on the lip of the pocket. It stopped just at the edge of the solar system.
Stuck in the lip of the pocket is a fantastic analogy. But mechanically, what actually stopped it from escaping entirely? The primary mechanism physicists propose is dynamical friction.
Break that down. How does friction exist in the vacuum of space?
Well, it's not physical rubbing friction, it's gravitational drag. In the very early solar system, before the sun's solar wind cleared it out, there was still a massive primordial disk of gas and millions of icy planetesimals out beyond Neptune. As this ejected 5th planet plowed outward through that debris field, its immense gravity pulled the smaller icy rocks toward it.
But the planet is moving fast.
Right, so as the planet flies past, it creates a gravitational wake of clustered material behind it. That clustered mass behind the planet exerts a backward gravitational pull, acting like an anchor.
Oh, I see.
This is dynamical friction. It bleeds off the planet's kinetic energy, slowing it down. Over millions of years, this drag slowed the ejected planet just enough to circularize its orbit and trap it permanently at 290 AU before the gas and dust finally dissipated.
Okay, I have a definitional question that I think a lot of people will be screaming at their speakers right now. If it's a rocky super-Earth and it's only 4.4 Earth masses, is it even officially a planet? I mean, everyone remembers the Pluto debacle. The International Astronomical Union downgraded Pluto because a planet has to clear its neighborhood of debris.
Yes, the classic neighborhood rule.
Right. If Planet 9 is floating out there in the Kuiper Belt surrounded by icy rocks, has it actually cleared its neighborhood?
It's a very valid challenge, and it's something Mike Brown, who ironically wrote the book How I Killed Pluto, is extremely firm on. The answer is an unequivocal yes. It is a planet.
Even at that massive distance.
Yes. The definition of clearing the neighborhood doesn't mean space is completely empty. It means the planet is the gravitationally dominant force in its orbital zone. Despite its massive distance, an object of 4.4 Earth masses exerts such immense gravitational control over the outer edge of the solar system that it dictates the orbits of everything around it.
Right, because of the hurting.
Exactly. It forces the ETNOs into resonances. It pushes objects out of its path. It is unquestionably the gravitational master of its domain. It easily satisfies the IAU definition.
So it's a planet. It's real, theoretically. Are there other origin stories besides the nice model ejection? Like, is it possible we just stole it?
Yes, the capture theory. Stars do not form in isolation. They form in dense stellar nurseries, clustered tightly together. In the early days of the sun's life, other stars passed very close to us. It is entirely possible that the passing star had a wide orbiting planet of its own, and the sun's gravity simply overpowered the other star and snagged the planet.
We kidnapped a super-Earth.
Or we adopted an orphan. Avi Loeb and Manir Siraj ran calculations suggesting our sun might have once had a distant equal-mass binary companion star that was eventually lost to the galaxy. If we had a binary twin, the combined gravitational net of the two stars would have been much wider, making it 20 times more likely that we could have captured a free-floating rogue planet that was just wandering alone in the dark.
All right, let's take a breath here. Because listening to this, the case sounds incredibly airtight. We have the gravitational footprints that are mathematically impossible to ignore. We have a highly refined suspect profile of a 4.4 Earth mass rocky world. We even have a mechanically sound origin story of how it got there via dynamical friction. It feels like a neat, elegant, undeniable package.
It does. It is a beautiful theory. But as an analyst of this data, I have to step in here and throw a bucket of ice water on the entire narrative, because not everyone in the astronomical community is buying a ticket on the Planet 9 train.
Area.
In fact, there is a fierce, highly technical, and sometimes deeply personal debate raging in astrophysics right now. The skeptics have looked at the exact same data Biddington and Brown are using, and they've concluded that Planet 9 is a complete phantom.
Right. Let's step into the skeptics' corner, because this entire theory, the whole house of cards, relies on one foundational premise, that these extreme trans-Neptunian objects are actually clustered together in space. But what if they aren't? What if they're everywhere and we just can't see them?
You've just articulated the concept of observational bias, and it is, without a doubt, the strongest, most lethal counter-argument against Planet 9. Astronomy isn't like standing in a perfectly illuminated room where you can see everything at once. Astronomy is like looking out of a tiny smudged window on a cloudy night while a spotlight shines directly into your eyes.
I've always thought of it like the streetlight effect. If you drop your keys in a massive dark park at night, but you only surge under the one flickering streetlight on the corner, because that's where the light is, you might find a few shiny objects there.
Right.
But if you assume that all shiny objects in the park only exist under streetlights, you were suffering from a massive lapse in logic. You only found them there because it was the only place you were capable of looking.
That is exactly what the skeptics, led by prominent astronomers like Samantha Lawler, are accusing the Planet 9 camp of doing. Think about the physical realities of finding these ETNOs. They are incredibly small, incredibly distant, and incredibly faint. We can only spot them when they are at their perihelion, their absolute closest point to the sun, because that's the only time they reflect enough sunlight to reach our telescope mirrors.
So we are inherently biased toward finding objects whose orbits happen to bring them close to us.
But the bias gets much worse when you factor in where we look. If you point a telescope at the plane of the Milky Way galaxy, the background is choked with millions of brightly burning stars and thick dust clouds. Trying to spot a tiny, faint, slowly moving rock against the blazing backdrop of the galactic core is practically impossible.
It's like trying to spot a firefly in front of a stadium floodlight.
Exactly. So what do astronomers do? They point their telescopes away from the galactic plane toward the darker, emptier patches of the sky.
We look where the viewing is easy.
Furthermore, we face seasonal biases. Telescopes on Earth are subject to weather. A major observatory in Hawaii or Chile might lose entire months of viewing time to monsoon seasons or winter storms. This means they only aggressively survey the sky during certain dry months, which strictly corresponds to looking at specific patches of the night sky.
So to synthesize Samantha Lawler's argument, she's basically saying, look, you found 6 extreme objects clustered together on one side of the sky pointing in one direction. But you only found them there because your telescopes were looking away from the Milky Way during the dry season, focusing only on the closest approach points.
Exactly. The skeptics argue that if you could magically remove all our weather and background light constraints and survey the entire 360-degree solar system equally, you would find these extreme objects pointing every conceivable direction. The clustering is just an illusion of our blind spots.
And the skeptics have the data to back this up, right? This isn't just a philosophical argument.
It is backed by massive, multi-year empirical surveys. Two of the most important are the Outer Solar System Origin Survey, or OSSS, and the Dark Energy Survey, DES. These teams spent years meticulously mapping the outer solar system. OSSS documented over 800 trans-Neptunian objects. DES discovered over 300 new ones.
That is a vastly larger sample size than the original 6 objects Biddington and Brown used in 2016.
It is, and crucially, the teams running these massive surveys did something very specific. They painstakingly modeled their own observational biases in software. They created a simulation and asked a simple question. If a population of extreme objects is actually distributed completely randomly in a uniform 360-degree ring around the sun, what would our specific telescope with our specific weather patterns looking at our specific patches of sky actually detect?
And the supercomputer spat out.
The supercomputer spat out exactly the clustering we currently observe in reality. Samantha Lawler and the OSSS team argue that when you rigorously account for these biases, the statistical evidence for orbital clustering vanishes entirely. The probability that we are just seeing a random distribution through a biased window jumps to 100%. She basically says the sample size Babbage and Brown used is far too small to draw sweeping, paradigm-shifting conclusions about the architecture of the solar system.
If Lawler is right, and there is no Planet 9 hurting them, how do the skeptics explain why these objects are on such extreme, detached orbits in the first place? Because they are still weird orbits, clustered or not.
The skeptics argue the extreme orbits can be explained entirely by known physics, specifically the migration of the giant planets early in the solar system's history. As Neptune slowly migrated outward billions of years ago, its gravitational resonances acted like a massive broom sweeping through the Primordial Kuiper belt.
Okay, so it swept them up.
Yeah, it temporarily caught icy bodies, dragged them outward into strange, highly inclined detached orbits, and then dropped them there as Neptune's migration stalled.
We don't necessarily need a hidden ninth planet to explain the mess. The violent history of the known giant planets is messy enough. I have to ask the uncomfortable human question here, because scientists are still people. Mike Brown's handle on social media was literally Pluto Killer. He wrote the book How I Killed Pluto. Is there a psychological element here? Does he just desperately want to be the guy who killed the ninth planet and then miraculously found its replacement? Is ego driving the simulation parameters?
It is an incredibly dramatic narrative, and it makes for great headlines, but it is vital to separate the personalities from the peer-reviewed math. Science is ultimately driven by data, and Brown and Badigan had just put their fingers in their ears and ignored the skeptics. They have directly engaged in a brutal statistical shootout with them.
How did they respond to the OSOS data? Because saying your data is biased is a heavy accusation.
In 2021, Brown and Badigan published a massive paper where they took the exact same observational biases that Lawler and the OSOS team highlighted, the telescope pointing constraints, the weather, the galactic plane avoidance, and they integrated every single one of them into their own rigorous statistical analysis of the known ET&Os.
They ran the skeptics' own parameters, and what was their conclusion?
They found that even when you aggressively, conservatively account for every single observational bias the skeptics pointed out, the probability of the clustering being a random fluke is still incredibly small. They calculated it to be somewhere between 0.2% and 0.025%.
So even with the bias, it's a 99.8% chance that the clustering is real.
Correct. Brown and Badigan argue that the signal survives the bias testing. They counter that the skeptic surveys, like OSOS, simply haven't looked deeply enough, or they tuned their bias simulations too aggressively, accidentally washing out a real signal.
So it's a standoff of the supercomputers. We have brilliant minds looking at the same icy rocks and coming to completely opposite conclusions. But let's play devil's advocate here. Let's step into the absolute deep end of theoretical physics. Let's say the skeptics are right about the planet, and Planet 9 is a ghost that doesn't exist. But the orbital clustering is undeniably real. If it's not a single massive planet causing this weirdness, what is it? Because the alternatives being proposed are about to get very, very weird.
If we rule out a single massive planet, theoretical physicists and astrophysicists have proposed some truly mind-bending alternatives that challenge our entire understanding of the cosmos. Let's start with the disk theories. Anne-Marie Madigan and Michael McCourt proposed something called the Zderick-Madigan belt, or the ZM belt.
That sounds like a sci-fi superweapon.
It is just as destructive to traditional orbital mechanics. Their theory posits, instead of one single 5-Earth mass planet, what if there's a massive, distant, continuous ring of icy debris, millions and millions of small objects, that together weigh up to 10 Earth masses?
Like the asteroid belt, but vastly larger and heavier.
Yes, and Madigan's incredibly complex models show that a disk with that much mass undergoes a bizarre physical process called an inclination instability.
Break that down mechanically. How does a flat disk become unstable?
It's driven by self-gravity. Over billions of years, the gravitational pull of all those millions of tiny icy rocks tugging on each other causes the entire disk to spontaneously buckle. It physically organizes itself. The gravitational resonance pushes the orbits of the individual objects up and out of the flat plane, shaping the entire disk into a massive cone.
And as they shape into a cone, their perihelia align. It naturally produces the exact clustering we observe, entirely through the swarm's own gravity without needing a big planet to hurt them.
Exactly. Another variation of this is the shepherding disk theory proposed by Antranik Sefilian and Jihad Touma. They suggest a 10 Earth mass disk of moderately eccentric objects acting as a giant gravitational counterweight to the massive inner planets, holding the extreme objects in place.
Okay, so the disk math works. Why isn't this the leading theory?
Because of the mass problem. It requires a staggering amount of material. Mike Brown and observational astronomers point out that when we look out into the Kuiper Belt, we simply don't see anywhere near enough mass to support a 10 Earth mass disk. The entire known Kuiper Belt is only a fraction of Earth's mass.
It would mean 99% of the material out there is completely invisible to us.
And beyond that, Konstantin Batygin argues it makes no sense developmentally. Why would the dense protoplanetary disk of our young solar system suddenly end at 30 AU, go completely empty for 70 AU, and then mysteriously restart with 10 Earth masses of thick material out beyond 100 AU? It defies everything we know about how solar systems form.
Okay, so if a giant disk is physically improbable, let's just break physics entirely. Enter MOND.
Modified Newtonian dynamics. It's a monumental shift in perspective.
Wait, hold on. How does the gravity of the Milky Way galaxy, which is thousands of light years away, suddenly overpower our own sun just because an icy rock gets a little further out? We are talking about rewriting Isaac Newton to explain a few weird rocks. Break down exactly how MOND works, because MOND is usually talked about in relation to giant galaxies, not our solar system.
You're right. To understand MOND, we have to talk about why it was invented in the first place. In the 1970s and 80s, astronomer Vera Rubin observed that spiral galaxies were spinning way too fast. Based on the amount of visible stars and gas in a galaxy, Newton's laws of gravity dictated that the stars on the outer edges should be flung off into deep space, like mud flying off a spinning tire. There wasn't enough visible mass to generate the gravity needed to hold them in.
To solve that, the mainstream physics community proposed dark matter, an invisible halo of mass that we can't interact with, providing the extra gravity needed to hold the galaxy together.
But in 1983, a physicist named Mordechai Milgram proposed a heresy. He said, what if dark matter doesn't exist at all? What if our fundamental equation for gravity, Newton's law, which says gravity strictly weakens with the square of the distance, is actually incomplete?
Milgram proposed MOND. He argued that at extremely low accelerations, the kind of incredibly weak gravitational environments you find at the very outer edges of a galaxy, the fundamental behavior of gravity physically changes. It stops weakening as quickly. It becomes slightly stronger than Newton predicted.
Yes. He introduced a new fundamental constant of nature called A0. If the acceleration drops below A0, gravity modifies itself to be stronger, holding the fast-spinning stars in place without needing a single particle of dark matter.
Okay, that's galaxies. How does the galactic scale theory apply to Planet 9?
In 2023, two researchers, Harsh Manther and Catherine Brown, decided to apply MOND equations to the outer edges of our own solar system. Way out past 100 AU, the gravitational pull of the sun becomes incredibly weak. The acceleration drops dangerously close to the MOND regime. The researchers found that under MOND, something called the external field effect kicks in. Because the sun's gravity is so weak out there, the background gravitational field of the entire Milky Way galaxy, the pull of the galactic center, starts to exert a dominating influence on the objects.
Wait, so the mass of the galaxy itself takes over?
Under MOND, yes. The math showed that this modified galactic gravity would slowly twist the orbits of extreme Kuiper Belt objects. Over millions of years, it would cause their orbits to naturally align and cluster toward the center of the galaxy.
And does that alignment match what we see?
It perfectly reproduces the exact clustering Trujillo, Shepard, Batygin, and Brown observed.
My mind is officially blown. But let's look at the philosophical weight of this.
Yeah.
To get rid of Planet 9, we are essentially trying to fix a leaky sink by tearing down the entire house of modern physics. We have to overthrow Newton, discard Einstein's general relativity, which doesn't play well with MOND, and throw dark matter into the trash. Are astronomers just inventing exotic sci-fi solutions because they are frustrated they can't find a simple planet?
It might feel that way, but it actually highlights a foundational principle of astrophysics. When you are faced with a stubborn anomaly, you must test every conceivable hypothesis, no matter how paradigm-shifting. You let the math lead you. But if you think overthrowing Newton is extreme, the most exotic hypothesis of all isn't MOND. It's the proposal published by Jakob Schultz and James Unwin in 2019.
The primordial black hole. I have been waiting for this. Lay it on me.
Schultz and Unwin suggest that the 5 Earth mass gravitational anomaly pulling on the outer solar system is not a rocky planet. It is not an ice giant. It is a black hole. But crucially, not a stellar mass black hole formed by the collapsing core of a dead star. This is a primordial black hole.
Meaning it was formed at the dawn of time.
Yes. Forged in the incomprehensible heat, pressure, and density of the Big Bang itself just a fraction of a second after the universe began. Microscopic quantum fluctuations in density collapsed in on themselves, creating trillions of tiny black holes that were cast out into the expanding universe.
And it would be tiny, right? If it has the exact mass of 5 Earths, how big is the actual physical event horizon of the black hole?
According to the Schwarzschild radius equation, a black hole with a mass of 5 Earths would have an event horizon roughly the size of a grapefruit, or maybe a heavy bowling ball.
A grapefruit-sized tear in space-time weighing 5 times as much as the Earth, silently flying through our outer solar system. This is exactly why I love astrophysics. But why would two serious physicists even suggest this? Is there any actual observational evidence for primordial black holes, or is this just pure math?
There is actual compelling observational evidence. There's a long-running astronomical experiment called OGLE, the Optical Gravitational Lensing Experiment. OGLE constantly monitors millions of background stars in the Milky Way, looking for microlensing events.
Explain microlensing for the listener.
Well, Einstein's theory of relativity proved that mass bends spacetime. When a heavy invisible object passes directly in front of a distant background star, the gravity of the invisible object bends the starlight around it, acting exactly like a magnifying glass. The distant star suddenly flares and brightens for a few days, then dims back to normal as the object passes.
And OGLE found a massive excess of these magnifying glass events.
They did. They found an unexplained swarm of microlensing events caused by invisible objects roaming freely through the galaxy. Crucially, the amount of magnification told them the mass of the objects. They were roughly the mass of planets, 5 to 10 Earth masses.
So there is a massive swarm of planet mass objects just freely floating out there. And Schultz and Unwin looked at that data and said, hey, maybe these aren't rogue planets at all. Maybe the galaxy is swarming with primordial black holes, and our sun's gravitational net just happened to catch one billions of years ago.
Exactly. And the primordial black hole hypothesis perfectly and elegantly explains one major frustrating detail: why we haven't seen Planet 9 with our telescopes yet. A grapefruit-sized black hole emits zero light, reflects zero sunlight, and radiates zero heat. It is fundamentally invisible to optical and infrared telescopes.
But wait, if it's the size of a grapefruit and it emits no light, how do you even look for it? You can't just stare into the dark.
You don't look for the hole itself, you look for the violence happening right on its edge. Surrounding this tiny black hole would likely be a microhalo of dark matter. As dark matter particles fall toward the event horizon, they collide and annihilate each other. This annihilation process produces a very faint, continuous glow of high-energy gamma rays.
So we look for a moving dot of gamma radiation.
Yes. Astronomers have actively scoured archival data from the Fermi Gamma Ray Space Telescope, specifically searching the predicted orbital path of Planet 9, looking for this specific slow-moving gamma ray signature.
But it gets even wilder than gamma rays. I read that Edward Witten, who is basically considered the modern Einstein, one of the greatest theoretical physicists alive, actually weighed in on this. He proposed a physical mission to find it.
He did. Witten proposed utilizing the technology currently being developed by the Breakthrough Starshot Initiative. The idea is to build a fleet of hundreds of microscopic wafer-thin probes, attach them to massive light sails, and blast them with giant ground-based lasers.
That's insane.
Yeah, the lasers would accelerate these tiny probes to a fraction of the speed of light, shotgunning them out into the outer solar system across a predicted orbit.
We just spray the outer solar system with laser probes. And what are they looking for?
We wouldn't be looking for photos. We would strictly monitor their radio telemetry. If one of those tiny probes happened to fly close to the grapefruit-sized black hole, the intense gravitational field would pull the probe off course, causing a tiny measurable delay in its radio signal back to Earth. We would literally feel the black hole in the dark.
A brilliant idea. Though I know Avi Loeb and others ran the math on that and calculated that the background noise from the plasma in the interstellar medium would probably drown out the tiny timing signal.
Yeah.
But still, the fact that Edward Witten is brainstorming ways to find this thing tells you exactly how seriously the highest levels of the physics community take this anomaly.
Absolutely.
Okay, so regardless of whether it's a rocky super-Earth, a mini Neptune ice giant, a massive disk of buckling ice, or a grapefruit of doom, people are actively sweeping the sky for it right now. How do you practically find a ghost?
Well, if it is a planet, finding it requires pushing our current optical technology to its absolute breaking point. As we mentioned, Planet 9 is incredibly frustratingly faint. Based on its distance, it is estimated to have an apparent magnitude of around 22.
To put that in perspective, human eyes can see down to about magnitude 6 on a perfectly dark night. The magnitude scale in astronomy is logarithmic and backward. Higher numbers mean fainter objects.
Mhm.
Pluto, which is incredibly difficult to see even with good backyard telescopes, has a magnitude of about 14. A magnitude 22 object is roughly 600 to 1,000 times fainter than Pluto.
And it's not just faint, it's practically motionless. Because it's 290 or 300 AU away, its orbital speed is incredibly slow. If it happens to be nearest aphelion, its furthest point from the sun, it would be barely creeping against the background stars.
It's like trying to spot a single black moth flying slowly in front of a dark, dense forest at midnight, and your only tool is a laser pointer.
So astronomers have to use incredibly clever indirect techniques to narrow down the search area, and one of the most brilliant methods involved the Cassini spacecraft.
Wait, Cassini orbited Saturn. Why are we looking at a probe flying around Saturn to find a planet billions of miles further out in the solar system?
Because gravity has infinite reach. It weakens with distance, but it never drops to zero. If a massive 5 Earth mass planet is lurking in the outer solar system, its gravity is pulling on absolutely everything, including Saturn. Cassini orbited Saturn for over a decade, sending back incredibly precise radio telemetry that allowed scientists to measure Saturn's exact position down to the meter.
Okay.
Astronomers took the Cassini data and looked for tiny, unexplained gravitational ripples, tugs pulling Saturn off its predicted course.
And did they find any?
No, but that negative result was incredibly valuable. By looking at what Cassini didn't feel, scientists were able to rule out massive swaths of Planet Nine's proposed orbit. They proved mathematically that Planet 9 cannot be in certain regions of the sky, or Cassini would have definitively noticed Saturn being pulled. This process of elimination pointed them away from vast stretches of space and focused their attention heavily toward a specific region near the constellation of Cetus.
They also looked at perturbations in Pluto's orbit, which offered similar constraints. And then there's the wild interstellar meteor data.
Yes. In 2022, researchers dug into the trajectory of an interstellar meteor that hit Earth's atmosphere, designated CEOs 2014-0108. They mathematically backtraced its trajectory out of the solar system and realized its highly unusual entry angle could be perfectly explained if it had experienced a gravitational swing by of Planet 9 on its way inward.
It used Planet 9 for a gravity assist.
Exactly. And tracking that trajectory backward pointed them toward the constellation Aries.
So we have these gravitational treasure maps pointing vaguely toward Aries or Cetus. How are we physically putting eyes on those regions?
Through a combination of brute force supercomputing and giant glass. At UC Berkeley, researchers aren't even using new telescope time. They're using supercomputers to mine the past. They use a technique called shift stacking.
Explain the mechanics of shift stacking.
Because Planet 9 is too faint to appear in a single standard telescope image, astronomers take thousands of archival images of the same patch of sky taken over several years. They know roughly the trajectory and speed Planet 9 should be moving. So the supercomputer digitally shifts each image slightly to compensate for that assumed motion, and then stacks all the images on top of each other.
It's like panning a camera with a speeding car. If you shift the images at the exact right speed, the background stars get smeared into streaks. But Planet 9, which was invisible in a single frame, stays locked in the exact same pixel. Its faint light builds up, photon by photon, image by image, until it pops out of the darkness as a bright dot.
Exactly. It requires massive computational power. But while the computers crunch the archives, observational astronomers are on the mountain peaks right now. They are heavily utilizing the 8-meter Subaru telescope at Mauna Kea in Hawaii. Subaru is unique because it has a massive primary mirror to catch incredibly faint light, but it also has a uniquely wide field of view, allowing it to scan large swaths of the sky rapidly.
But the real game changer, the ultimate weapon in this hunt, is about to come online.
Yes, the Vera C. Rubin Observatory in Chile. This is the telescope the entire astronomical community is waiting for. It will conduct the legacy survey of space and time. It is equipped with a mind-boggling 3,200 megapixel camera. It is designed to photograph the entire visible night sky every few nights, generating a continuous, high-definition time-lapse of the universe.
And the 2025 Siraj study specifically noted that their newly refined, closer 290 AU orbit for Planet 9 places it squarely within the field of view of the Rubin Observatory's early operational parameters.
If it is a physical planet, and it is out there reflecting even a handful of photons, the Rubin Observatory possesses the sheer optical power and the wide field mapping capability to finally catch it.
Even citizen scientists are getting in on the hunt. Projects like Backyard Worlds on the Zooniverse platform allow literally anyone with a laptop to flip through thousands of infrared satellite images looking for moving dots that the computer algorithms might have missed.
It is a massive, crowdsourced, collaborative human effort to map the absolute edge of the darkness.
As this search reaches a fever pitch, I have to ask, if someone finds it tomorrow, if Vera Rubin snaps a photo and there it is, what do we even call it?
Well, the International Astronomical Union has very strict nomenclature rules. The discoverers generally get priority to propose a name, but for major planets, tradition dictates it has to be a prominent figure from Roman or Greek mythology.
Vatican and Brown have joked in interviews about calling it Jehoshaphat or George. George is actually what William Herschel originally wanted to name Uranus to honor King George III, which thankfully got vetoed. Brown has admitted they informally call the simulation fatty among themselves because of its massive initial weight.
On the more serious side, physicist Lorenzo Iorio suggested the name Tellisto, derived from the ancient Greek word for farthest. Others have heavily pushed for Persephone, the wife of Pluto in mythology, though that name is technically already taken by a main belt asteroid.
My favorite naming controversy involves Alan Stern. He is the planetary scientist who led the incredibly successful New Horizons mission to Pluto. He absolutely hates the term Planet Nine. He views it as an erasure of Pluto's history and a direct insult to Clyde Tombaug's legacy. He vehemently demands the scientific community call it Planet X or Planet Next until it is officially confirmed and named.
The politics of planetary naming are almost as vicious as the orbital mechanics.
Mm.
But whatever we call it, its discovery would fundamentally rewrite our understanding of our solar system's history and our place in the universe.
Okay, let's bring this massive journey all together. We started with the triumph of Neptune and the false dawn of Pluto. Where are we today? We have undeniable, heavily debated gravitational footprints left in the cosmic snow by Sedna and a cluster of extreme icy objects. We have a highly refined supercomputer-generated suspect profile, a 4.4 Earth mass super-Earth, carved out and trapped by the chaotic billiards of the early solar system. We have fierce statistical warfare over invisible biases, streetlight effects, and telescope pointing. And we have an ongoing global sweep of the darkest parts of the sky using the most advanced technology humanity has ever built.
And as we close, I want to leave you with one final, deeply provocative thought about what happens if we do find it, and it turns out to be that wild alternative.
Let's hear it.
If Planet 9 turns out to be a primordial black hole, as Schultz and Unwin suggest, it wouldn't just be a new planet added to a textbook. It would mean we have a pristine, untouched artifact from the very first microscopic fraction of a second of the Big Bang, trapped in an orbit right in our solar system's backyard. We wouldn't just be looking at a new icy world, we would be looking directly at the violent, unfathomable origin of the universe itself, suspended in the dark, close enough that humanity could feasibly send a probe to touch it.
That is heavy. It changes the entire context of the search. Right now, we are staring out into the murky, blurry edges of our solar system, trying to squint through the data to see if the math is broken or if a shadow is real. But whether it's a rocky super-Earth, a massive buckling ring of ice, or a grapefruit-sized tear in space-time, the math insists something is pulling in the dark, and we won't stop looking until the picture is crystal clear.